Good evening to all and welcome to our International Physics webinar. Today it's our 280th International Physics webinar, and we have with us here today Dr. Professor Sokrates Pantelides from the University of Vanderbilt, USA, and he has already connected with us. So I'd like to welcome our speaker, sir. Good morning to your part and good evening to here, and thanks for accepting our invitation. It's a good opportunity for our student and viewers to interact with you through the StreamYard and the online platform. So I think you have already come to know the title of this today's webinar, and title is very exciting: A Journey in the World of Nanoscience and Nanotechnology. And our speaker is Professor Sokrates Pantelides, working as a professor, Department of Physics and Astronomy, and also Department of Electrical and Computer Engineering, Vanderbilt University, USA. So before going to him, I would like to introduce him with you all. So he has completed his primary school, schooling mainly in Cyprus, and then he completed his bachelor degree in physics from the Northern Illinois University in 1969. He has completed his MS in physics from the University of Illinois in 1970 and his PhD degree in 1973 from University of Illinois. And his thesis advisor was Professor C.T. Shaw, and his thesis title was Theory of Point Imperfection States in Semiconductor. Fields of interest: theoretical physics, semiconductor physics, first principle atom scale, applied density, functional theory. We can see his current appointment. Currently, he's working as an university distinguished professor of physics and engineering, Vanderbilt University, from 2010 to present, and also working as an William A. and Nancy F. McMinn Professor of Physics, Vanderbilt University. And he has been working this post from 1994. And he's also working as a professor of electrical engineering from 2008, and also work as a distinguished visiting scientist at Oak Ridge National Laboratory from 1995, and also work as a distinguished visiting professor, University of the Chinese Academy of Science, Beijing, China. And we can see his professional society. He's a member of American Physical Society, American Association for the Advancement Science, Materials Research Science Society, in Institute of Electrical and Electronic Engineering, and Electrochemical Society. And professional award, he got elected fellow of the American Physical Society in 1980, and IBM Outstanding Innovation Award in 1981, invited by the Swedish Academy of Science to nominate candidates for the Nobel Prize in Physics annually since 1982, Chancellor's Research Award, Vanderbilt University in 2003, elected fellow of the American Association for the Advancement of Science in 2003, APS Outstanding Referee Award in 2008, elected fellow of the Material Research Society in 2012, elected fellow of Institute of Electrical and Electronics Engineering in 2014, and appointed fellow of the Kavli Institute of Theoretical Physics in Beijing, China in 2017. So I think you will enjoy this session. So sir, thanks again for joining with us, and it's your time. You can start your session, sir.
Thank you, and hello everybody. I am truly pleased to be able to give you this presentation. I hope you enjoy it. It's a journey in the world of nanoscience and nanotechnology, a field that has been with us for more than 20 years now, and it's still at the edges and frontiers of material science. In order to understand what the nanoscale is, it is best to understand atoms. And I'm sure you all know about atoms, but we will see some new aspects of them perhaps today. It all goes back to this fellow here, Democritus, in Greece, in ancient Greece, a long time ago, 2,500 years ago. The word atom is a Greek word, atomos, which means uncuttable. He had the brilliant idea that if you cut matter up into pieces and keep cutting it and cutting it smaller and smaller, That must be an end to this process, that there is something that ultimately is uncuttable. And everything then is made out of these objects. He did not have a great view of what these objects really are, what are they made of. He did believe that they exist in what he called the vacuum, but the other philosophers in Greece didn't quite like those ideas because they thought vacuum means something that has nothing in it. We know most about him from Aristotle. His books have not survived to today, even though he wrote many of them. And the concept lay there for more than 2,200 years until John Dalton, who revived the idea, and he proposed that atoms are solid, massy, hard, impenetrable, and too small to be visible. And he was wrong on most those things. They are not impenetrable, and they are not too small to be visible. I will show you pictures of them. But he had the ideas that compounds are compound materials. They knew of materials that had more than one element in it. By the 1800s, the idea of elements and the beginnings of the periodic table of the elements was there. So compounds are made of different types of atoms, and that chemical reactions are rearrangements of atoms. He didn't really know how atoms connect together. He had these visions of hard, solid spheres that have some kind of hooks on them. This is a schematic of what he thought vaguely, but even Democritus had some ideas of hooks. They couldn't really imagine other more complicated things. And the structure of the atom was starting to come about in the late 1800s when the electron was discovered first by J.J. Thomson at Cambridge in England, and then Ernest Rutherford and his students with experiments of shooting alpha particles on gold foils realized that the atom must be made by a hard nucleus and negative charge, so positive and negative charge. And the original idea was actually that the nuclei are like raisins in a raisin bread, where you have the raisins in the middle of the opposite charge. It wasn't until 1913 when Niels Bohr had the idea with mathematics attached to it that the electrons are actually particles that are buzzing around the nucleus like the planets around the sun. This is also wrong, even though Niels Bohr got the Nobel Prize. He deserved it thoroughly for his ideas. And then it developed further by Erwin Schrödinger when he wrote down the Schrödinger equation. And now we know that we have a nucleus at the center and a fuzz of an electron cloud around it with the predominant probability of being found at a certain radius in a shell, not in an orbit. So this is the modern picture of an atom. How small are atoms? We start with the human hair and go down to a single hair, and that hair is what we call 100 microns, which is 1/10,000th of a meter, or 100,000 nanometers. So on the scale of nanometers, the hair, human hair, is quite thick. There are across that hair 200 to 500,000 atoms. And the nanoscale is objects that are at least in one dimension between 1 and 100 nanometers. And that is objects that may have 200 to 500 across in that particular dimension, or 2 or 3 dimensions where they are very small. So if they are smaller than 10 nanometers in any particular dimension, that's only 20 to 50 atoms across. And we know today that we can have sheets of atoms that are only 1 atom across. We'll see of those. A history of the nanoscience and nanotechnology legitimately goes back to 1959, when this gentleman, Richard Feynman, a very notable physicist of the 20th century, wrote an article called "There is Plenty of Room at the Bottom." And he thought about scaling letters to fit the entire Encyclopedia Britannica at the head of a pin. And he was thinking of mechanical means at the time. Computers were not at that point functioning, even though there was some huge computers at the time. Tensor computer circuit could be to make small computers. He didn't really had a good vision about how small a computer can be as we know them today. He was thinking of tiny tools, mechanical tools that you could make things with. And but he did believe that microscopes that at the time could not see atoms, he said, if you make them 100 times more powerful, you should be able to see atoms. And I put see in quotes because seeing with our eyes and seeing, there are other ways of seeing as well through the microscope. And ultimately, he said you can manipulate atoms to create tiny structures. And ultimately, to swallow the doctor, to be able to put something inside the human body through which you could see what's in there. Most of these things have come to pass. We do them all today. He was a great visionary. And then more recently, science breakthroughs in the 1980s and 1990s brought us to nanoscience and technology at the end of the 20th century. By using lasers, very, very powerful, energetically powerful lasers, striking materials like silicon and others, they were able to produce what we call today nanoparticles. You just break it up into smithereens. You scatter everything, and you can measure them with mass spectrometers and find out that these nanoparticles used to be about 550 nanometers across. Another major event was the discovery of fullerenes by Karl Kroto and Smolny, who got the Nobel Prize in 1996 for them. The discovery was in the 1980s. And carbon nanotubes, which is both of these are like chicken wire of hexagons, and in the case of the fullerenes, pentagons, arranged carbon atoms, and the diameters of these carbon atoms are 10 nanometers and various others smaller than 10 nanometers and larger than 10 nanometers. And finally, in the 1980s, as the scanning tunneling microscope, which we are going to discuss later, was able to see atoms, and this is not the first time that atoms were seen. We'll walk through that history a bit in a minute. So those things were happening in the 1980s and the 1990s, and many funding agencies in the federal government in the United States got together and made the case to the Congress and to the president, along with engineering and scientific societies, and they had a vision of a future in which the ability to understand and control matter at the nanoscale leads to a revolution in technology and industry that benefits society. And they were thinking of passive nanostructures, active nano devices, complex nano machines, productive nanosystems, all on the scale that we saw how much smaller than the thickness of the human hair. Initial funding started about the year 2000. To date in the United States, 25 billion have been spent on nanoscience and nanotechnology, and currently 1.5 billion per year solely from the federal government. And in the rest of the world, there is a lot of funding and among companies. One of the key elements of nanoscience, of nanoparticles, is an example here of gold nanoparticles. If they are fairly large, you see the gold color if you have them in a solution that is otherwise clear. You put the nanoparticles in there, you see a nice gold color. But if they become smaller, if the nanoparticles are smaller, you get the small ones to be awarded 20 nanometers or less, their color changes to red. Obviously, something is happening in the world of nanoparticles. This is another example of research that was done by Sandy Rosenthal, a chemistry professor here at Vanderbilt, cadmium selenide nanoparticles in solution of different sizes if they are 66.5 nanometers. So we are getting very small now, very nano. The color is red. Then at 4 nanometers, it turns to yellow. And you can see the colors of the rainbow, right? Then you go to green, light blue, and dark blue at 2 nanometers. And as they tried very hard for a long time to make nanoparticles smaller than 2 nanometers, and it was very difficult. They expected, of course, to get darker blue or purple at the end of the rainbow colors. The surprise, big surprise in 2005, that when they got nanoparticles of cadmium selenide smaller than 2 nanometers, the color was white. Nobody understood that for a long time. The color change is understood by quantum mechanics in terms of the energy gap that the electrons have to jump in order to emit the color, and that band gap depends on the confinement that the electrons have. When you confine them in a very small space, they behave differently. But why white light was a mystery. And my group, we actually explained how it works through a combination of microscopy and theory, and I will tell you about that later when we introduce microscopes. Another example of nanoparticles that made a little noise was that if you look at gold surfaces, as you know, are inert. They don't interact with anything. Gold doesn't oxidize or doesn't do anything. But if you go to gold nanoparticles, very small nanoparticles, they act as catalysts and enable CO oxidation. You can see the gold nanoparticle here, a CO molecule attached to it, and an oxygen molecule from the atmosphere is attached to it. And they managed to get them together to form carbon dioxide, which is a good, unlike CO is poisonous and is generated on many different occasions, and you want to capture it into carbon dioxide. Platinum does the opposite thing. Platinum surfaces catalyze CO oxidation, but platinum nanoparticles do not. Again, this is an example from my group, and this is an example to show that theory plays a major role in the nanoscale science and technology. We discovered through calculations and simulations that gold nanoparticles are fluxional. That means the gold atoms are not solidly bonded, but they rattle around, move around, and as they move around, they bring the CO and the O2 together and they react. In contrast, the platinum surfaces are capable to do the oxidation, but when you go to the nanoparticle, it's extremely tight. The bonds are much stronger and they hold together. So when the CO sits there and the O2 sits there, they don't get together to react. So nanoparticles are used for many things, like we just saw about catalysis. One of them is to targeted drug delivery. You can make hollow nanoparticles and put drugs inside them, and whatever the material here may be. Then you can attach organic molecules, and if you put the nanoparticles in the human body, in the blood, they can move around in the human body in a harmless way, and these molecules that are hanging out have preferences as to where they will attach themselves. So a lot of research is done. You choose the molecules to get the nanoparticles to attach in parts of the human body, inside the human body, where it's desirable, and then they can release the pharmaceuticals, the medications that are inside, directly at the spot where they are needed. Nanoparticles are used extensively or in many experimental procedures, and in some that have been tried and proved to be true and are used today to actually do therapy, cancer therapy, and cure cancer. Here's an example of a nanoparticle with gold nanoparticles attached to it. Gold nanoparticles are very optically active. They can absorb light and re-emit it, and that can actually burn the cancer molecules. They are used successfully, but not widely yet, to cure prostate cancer in human males. Another example that is done by a company called Nanobiotics for a tumor that is on this inside the skin, right under the skin. If you do conventional radiation therapy, the X-rays go everywhere, and they do collateral damage around it's not big, but around the tumor. So to avoid the collateral damage around the tube, they inject high Z nanoparticles inside the tumor. Z is the atomic number. Atomic number is low in the periodic table, in the lower columns of the periodic table, like hafnium. And they have a lot of electrons. If you understand the structure of the atom, there are electrons at the core that are very deep in energy, and they are very efficient absorbers of X-rays. So you can shine a relatively small dose of radiation, and it gets absorbed by the nanoparticles and gets re-emitted right inside the tumor. Here's experimental variation. This is the usual dose delivered to the cell at this level. And if you deliver the same dose, then you would get the re-emission to be 9 times higher. So you can, 9 times higher, so you can be far more effective in killing the tumor itself, because the nanoparticles re-emit the X-rays inside the nanoparticle. This is another example of nanoparticle use in sunscreen, the original sunscreens that you put on your skin to go to the beach and swim and be struck by the sun. By using titanium oxide or zinc oxide nanoparticles in the sunscreen, it becomes more effective, but you also do not scatter the reflected visible light, and therefore makes the sunscreen invisible instead of putting this white gook. There was a lot of controversy 20 years ago that by people who claimed that titanium nanoparticles are bad for you and they can cause cancer. All of those things were proved incorrect, and these things are quite safe. Smart textiles. I could give you a whole talk on smart textiles, that you can use them to behave differently when they don't get wet, or they warm you, or they can firemen can use gloves that are totally safe not to burn their hands when they take very hot things, and all kinds of other. Here's an example of mosquito repellent cloth that was advertised by this model. But it's not, nanoscience is not only nanoparticles. Nanowires is another big deal, where the wires are extremely thin. Now, if you have a cold reservoir and a hot reservoir, so you have a difference in temperatures between the two, you can actually generate electricity from them. So you get the hot matter to go through like that, and it's a little bit like a battery. It's just that the one pole is hot and the other is cold. Geothermal heating is done today in a variety of ways with big pipes and everything else, because the Earth's surface can have one temperature, but down underneath, if you go 7 to 10 meters, depending on where you are on the globe, the temperature can range between 10 and 15 degrees Celsius, and it's always the same in that range. And whereas the Earth's surface can get very hot, as you know, in many parts of your part of the world can get extremely hot, 40 and even 45 and 50 degrees Celsius, so you can have a good gradient. The Mediterranean temperature, it ranges in temperature only over 10 degrees, again, depending on where you are, whereas, of course, the air temperature can be much higher and much, much lower. So there are many options. The question is to have efficient devices Efficient devices are very difficult to make, and the efficiency is proportional to the electrical conductivity and inversely proportional to the thermal conductivity of the material that you are going to use. Normal metal wires do not work, but there is a lot of research in thermoelectric materials. And if you make nanowires, you get many benefits from it. Here's an example of a device where these are where everything is very tiny, and you have the heat reservoir in the red and the cold reservoir in the blue here. And you have to use N-type and P-type nanowires, which, if you don't know what they are, don't worry about it. It's different impurities inside the nanowire to change the way electrical conduction occurs. But that's an example. And then something very big happened in 2004 to take us beyond nanoparticles. And that's the realization that graphene, which is a single layer of graphite, this is graphite, and it's what is called the lead in pencils. What you have in your pencil is not lead, it's graphite, which is carbon atoms in sheets, as you see here for the graphene. This is a schematic, and they are stuck like that. And the bonding between the sheets is very weak. So these sheets can slide around. And that's why graphite is a lubricant, is used as a lubricant. And that's why your pencil can write the way it writes, because you are peeling off these things and sticking them to the paper. And since then, since 2004, there has been an explosion of two-dimensional materials. And Novoselov and Geim at Manchester, England, got the Nobel Prize for it in 2010. Since then, we've had hundreds of single layer materials, and the layer is either one sheet of atoms. There are quite a few of these. Boron nitride is another one where you replace carbon atoms by pairs of boron and nitrogen. But many so-called monolayers actually have several planes of atoms, 3 and 5 and even more. And they are made from materials that are naturally layered, like graphite, that has these layers with weak forces connecting them. So on the nanoscale and nanotechnology from which, so you use materials, nanomaterials, to make new technologies. We have nanoparticles. Quantum dots are a form of nanoparticle, and we call this zero-dimensional because all 3 dimensions are nanoscale, so they don't have a big dimension. Nanowires or nanotubes, nanoribbons have 1 dimension that is microscopic. The other 2 are nanoscale, and ultimately the 2D materials have 2 dimensions that can be large. But one of the dimensions, the thickness here, is nano on the nanoscale. So we call them 2-dimensional. Using all these nano components, you can make nano devices, you can make electronics, light-emitting diodes, solar cells, all kinds of other things. You can make nanostructured materials where the elemental pieces of the material are on the nanoscale. And you can develop nano processes like nanocatalysis, nanofluidics. Nanomedicine is a big deal to use, as we said, as we showed earlier, nanoparticles and graphene and other things. They are used in batteries now, and the lithium-ion batteries that are rechargeable as opposed to non-rechargeable batteries have a lot of components that are on the nanoscale. Ultimately, the biggest thing that has reached the nanoscale is what we call transistors, that are the elements in integrated circuits that make your computer function, and everything else. Just about everything has chips in it that are little tiny computers. This is the size of individual transistors of that used to be in 1970 when this whole process started. There were 10 microns and gradually went to 1 micron. This is a logarithmic scale, 100 nanometers, 10 nanometers, and we are down now to 5 nanometers. And there is, of course, a limit to how far you can go. This may flatten out, but the nanoscale at its ultimate, it's being reached now there like that. And this nanoscale is what has produced iPhones and other phones today, smartphones, and all the incredible things that we have that you hold in your hand is an entire computer, and the electronics, optoelectronics and other things that run the networks and the internet and everything else. At the age of young students, like most of you are not familiar with how the world was before that and what kind of computers we had. And I will give you a glimpse of that because I was there. This was a computer in the 1980s. The price was close to $10 million. It filled up a big room. You can see the size from the chairs. And the memory that it could access to do computation was only 32 megabytes, okay? And we had peripherals like disk storage to store information, laser printers that were large, drum plotters, and tape drives. I will show you the size of those things. IBM disk storage in the 1980s, 2.7 megabytes per square inch. It totaled 2.5 gigabytes. It was the size of a refrigerator, as you can see here, and the price was $100,000. Today, you can buy 2 terabytes of memory, right, for about $20, and it fits in your pocket. This is just a right now they can make them as much as small as a centimeter, and so on. They can make them smaller, but then you wouldn't be able to function, to operate them, to play with them. This was the Calcom plotter that I used. One of these when right after I got my PhD degree, they came on the line. I was a postdoc at Stanford University, and what you have here is a drum, and there was paper on it, and it was funny kind of paper, and you have a pen, and the pen could slide back and forth, and this thing would rotate and made noise. Let's see if we can see it. There it goes. This is how you plot it. This was 1970. Oh, I hope I can get back now. Pretam, how do I get back?
Sir, minimize that page. Come to PowerPoint page. Come to the PowerPoint. Minimize this web page. Not here, not here, not here. Minimize the web page and click the PowerPoint.
Ah, okay,
Yes.
excellent.
Yes.
Okay, and just for a joke, I don't know how real this was. There is confusion about this. It exists on the web somewhere, but this was a 1954 vision of scientists from the Rand Corporation as to what a home computer might look like in the year 2004. From 50 years later. And you can see it wasn't a very good guess. And they said that with teletype interface, which is this concoction here, and the Fortran language, the first language that was used to program computers, the computer will be easy to use, they said. Well, they missed out completely. So now I'm going to switch gears and say, can we see nanoscale structures? Can we see atoms? Yes, but not with an optical microscope that it works with light. And you may know how a microscope works, and this is the difference between seeing with your eyes or taking the signal onto a computer screen and seeing on the screen. Okay, that's equivalent. And both are doable for optical microscopes. You have a lens, you have your eye there, and you know the mathematics of how you can take an object that is small and make it appear to you with using the lens to bend the rays to see it big. A transmission electron microscope using electron beam instead of light was first made by Ernst Ruska in 1930 and Max Noll in 1931. Noll had died before the Nobel Prize was awarded to Ruska in 1986. And as you can see, similar to the optical microscope, the specimen is there, and you have these rings that behave as lenses. These are electromagnetic lenses, not glass lenses. And we have an eye there, but again, you're not going to look with your eye on these things. In the old days, they had to, but now you have the computer images. And in 1970, Albert Crew developed a scanning transmission electron microscope, which is a focused beam that you scan, and you have a film, and we know the atoms now inside are planes of atoms in a solid. You have a thin film, and as you move it around, you collect the scattered rays here, and you actually construct an image like a photograph of what you can see. He was the first to see atoms back in 1970, but not very well. Now you go back to Feynman and his dream, and in 1959, it was around here on the green line. There were microscopes that actually could do a resolution of 1 nanometer, but he wasn't aware of them at that time. They hadn't been announced, perhaps. He only knew about 10 nanometers. And he said, if you remember, that you can make them more powerful. There's now laws of physics that forbid you, and be able to get the resolution increased by 100 times. So you can see objects that are 1/100th of what it was possible to see at the time. Since then, we've had so many developments and aberration corrections, which is fixing problems of the electromagnetic lenses, the same way as the glass lenses don't quite focus all the rays in one point. The same thing, you need corrections. Aberration corrections have advanced up to 8-fold, and now the resolution is actually gone way beyond what even Feynman dreamed. We are really down on the very, very, very small distances between atoms, below the 10th of the nanometer. And here is a picture of graphene with this scanning transmission electron microscope by my friend Wu Zhu. You can see how bright they are. And these are really photographs, if you will, of individual atoms from which the electron beam is scattering and generating an image. And this distance here between atoms is 1/4 of a nanometer. Here is a case where my friend found a defect that had 6 atoms in it that were identified as silicon atoms. And they took so many pictures of them, they realized that one of the atoms was moving, and they made a movie out of it. And if you saw carefully at one point, it looked like there was half an atom over on the left and half an atom on the right. Watch it again. There. What is going on? It's not that a half an atom is over there and half over here. It's that the image is taken by scanning like this. So when you go this way, generating the image, the atom is over on the left, and then you come back and the atom is on the right. So the picture that you get, it looks like the atom is split. Okay. There are a lot of other examples that I will show you, but I will demonstrate a number of things. I'm going to show you atomic resolution videos like the one before of nanofabrication, of actually using the electron beam to create things. This is my student, Junhao Lin, about 10 years ago, who used the electric beam in a monolayer of molybdenum disulfide. And you see the atoms there, and you use the beam to image and also manufacture or fabricate. You drill a hole with the beam because it's so strong. You keep it there, you can drill a hole. You make the hole bigger, then you make another hole, and you make it bigger, and ultimately you end up with what you would call a nanowire. This is pretty fat, but you can thin it down, and you can see it being thin here by the electron beam while it's being imaged. And all of this, of course, is manipulated by computers. You don't use your hands to do anything. It's all by software, and you guide the software. So you can see how the electron beam makes the nanowire thinner and thinner. This is MOS2, molybdenum disulfide. I will show you molybdenum diselenide. The colors are the choice of the artist. These are just electrical signals, and they are reconstructed into an image. And this one is even more fun to watch. Look at how strong it is. The electron beam is beating it up, and it's not falling apart. And at one point, it peels off, and you're down to to 3 atoms across, and you can see it gets beat up, but it doesn't break, just 3 atoms across. And we calculated that these nanowires are metallic, which was very significant, and we demonstrated subsequently with experiments that they are metallic. And this is back to MOS2, by making junctions like that, and these nanowires being metallic, you realize that you can build devices on a monolayer and then be able to make nanowires on the monolayer and connect them so that you can have a circuit on a monolayer. So these are visions of the future where electronics may go someday. A lot of devices have been fabricated on two-dimensional materials and some small circuits. But we are going to go to electronics. You'll see how many circuits you need to have functioning computers. So I'm going to show you now how you can fabricate new nanomaterials, not just nanowires. And then we can do physics by combining theory with microscopy to explain what happens at the nanoscale. Here is a layered material, palladium diselenide, and it's layered like this. This is the individual planes, the individual layers that have 3 planes of atoms. And you can thin it down to this is theoretical analysis now that says in principle, you could thin it to 3 layers, to bilayers and monolayers. And a number of people studied the properties of the monolayer. But again, my former student, Jun Hao Lin, he thinned the material with the electron beam in the microscope to bilayers and monolayers. But the big surprise was the structure of the monolayer was not what it was expected. If you look at the bilayer region, it looks like this. The STEM image is like this, and the STEM simulation is like this. From the structure that is understood, the structure of the material, everything was fine down to the bilayer, but the monolayer wasn't like that. The monolayer had a completely different image, like this. And if you look at the material, what it should be, the STEM simulation said that the image should look like this, which it does not. So this was not a known structure, and we used calculations of quantum mechanics, using quantum mechanics, and we tried with the monolayer to remove a bunch of selenium atoms, which is believed that the electron beam can knock out selenium atoms, preferentially over palladium atoms. And we couldn't find anything that would match the image. We tried a bilayer and studied the possibility of how the 2 bilayers might join together to form a new monolayer. And we demonstrated that by removing seleniums, the distance between the layers decreases more and more. And when they decrease enough, the upper layer and the lower layer, the electron distribution, which is in this yellow color, when they get very close, when you have a lot of selenium vacancies, they form bonds between them, and they lead to a new structure. We identified the structure, we did the STEM simulation, and it matched this. So we did more things with this material, but it shows you how you can generate a new material. Now I'm going to show you another example where STEM imaging and theory together can explain what happens on the nanoscale. I'm going to do this. Remember that I told you that when they did the smaller than 2 nanometers, they got white light, and it was a mystery. One of my students who was doing microscopy and theory, and Sandy Rosenthal students, also participate in these experiments with the microscope. They made the samples, and they did part of the microscopy. My student did the theory, and here is microscopy and theory. Here are the nanoparticles. You can see how uniform they are. And when we look at them closer with the microscope, you can start seeing their crystalline structure. And even closer at the, this is the scale for 1 nanometer. So these are larger than 2 nanometers, and they are crystalline. And then they get fuzzy at the edges. But when you get smaller than 2 nanometers, they are not crystalline anymore. And you can see also that they are very fluxional. They made a video of them, and the atoms are bonded together, they stick together. This is 2 different nanoparticles, but they are very fluxional again. Remember the fluxional from the gold nanoparticles. We did the theory of this. We took using the big computers that we call, in quotes, the theoretical microscope. And here is our nanoparticle made of 70 fine atoms, cadmium selenide. If we put them at room temperature, and in order to get the white light, you have to strike them with UV light of 4 eV. We looked at if we give a nanoparticle like that, the energy that it would get from the light that they used to do the experiments and get the white light, it is also fluxional. You can see what is going on. The atoms are not crystalline. We started them in a crystalline form, and then they get messed up and vibrate like this. And we were able to actually calculate what light such fluxional nanoparticles would emit, and they would emit the whole range of energies. And you know, when you emit the whole range of photons, if you superpose all the colors of the rainbow, you get white. And we calculated the spectrum of what you would measure. The different colors are inside here, and they are superposed on your eyes very quickly. And therefore you see white, and the experimental spectrum was like that. So we explained everything to the great detail. Okay, the other microscope, the scanning tunneling microscope, invented by these folks at the IBM Zurich laboratory in Zurich, Switzerland in 1986. They got the Nobel Prize. It came out in the early 1980s, so the Nobel Prize was very quick. And this is a tip that gets scanned on the surface, and you are imaging by using the tunneling current of electrons from the substrate to the tip. These are the atoms on the tip right there. And I saw you this image before. Here is an image of a nanotube. And Don Eichler in 1989, using the tip, was able to push xenon atoms around on a nickel substrate and push them around to form the letters IBM, push them around to form a coral. And here I'm going to show you a video that was made. These are all individual atoms, and it's a lot of fun to watch. And we're going to go to YouTube again. These are images that were formed with the STM by pushing individual atoms one at a time and making these images, photographing them on the microscope, and then combining them to make a video. It was made by moving actual atoms frame by frame. These are all atoms. The music is added. Ping pong. And trampoline. This is an image of a nanotube, and think is the word logo of IBM. Okay, let's see if we can get back again. I'm here. Okay. Now, this is work done in Beijing by my collaborators
look up
there.
in the sky and see the stars and
Oh my goodness.
nebulas and other galaxies with a telescope, and be excited by the strange, interesting patterns the universe forms.
YouTube is still on.
We can also look in the other direction, down towards the small, and see new and strange and exciting patterns that are formed by these pieces of the universe that we're all made out of.
You know, we're trying to make a movie using atoms, and so that sounds like a simple concept, but in reality, of course, these atoms, it does take some concentration because you want to get them in exactly the right spot.
I don't know how to kill this.
We have a tool that allows us to move atoms on surfaces and build
Just
structures on atoms time.
stop that video.
Or how can we use
Okay, sorry, I think he has disconnected. So please give us time to reconnect. Thanks for your patience.
I lost you.
Yes. I sent email when you
I
lost
didn't
me.
see.
Okay.
Are they still there? Do you want me to go back where I was and finish, or do you want to just ask questions?
Yeah, you can say something in the last slide where you were before lost the connection. You can go the slide, no problem, and talk maybe about 5 to 10 minutes.
I think I lost you.
After the YouTube video. So
Yes. I lost you here.
so you have to share again because we can't see your
Okay.
just come. Yeah.
Am I sharing the right screen?
We can't see anything yet.
Oh, my screen froze.
So can you see this StreamYard page?
My screen, my PowerPoint has frozen.
Oh, okay. Okay, then we can.
I don't know what. Wait a minute. Can you see now? Do you see my screen?
You have to share. We can't see.
How is that?
Yes, now we can see.
Okay.
Just hide here. Minimize it or hide.
How do I get rid of this?
Just minimize minus sign. Click the minus sign. Minus sign. Yeah. Yes.
Okay. Okay. Here I was showing you how the scanning tunneling microscope, in addition to pushing individual atoms around, you can use the tip to pick a piece of graphene. This is a piece of graphene, and you can fold it over and then unfold it without any damage. This was first accomplished by my collaborators in Beijing in 2020. And you can see here, once you fold it, you have a nanotube-like structure. And then over here is a bilayer graphene. And you can control the angle of the bilayer graphene, which then would have different properties. So there is a lot of potential here for fabricating individual devices. But of course, it's not quite a tool that you can manufacture large numbers of these things very easily. So it's more of a scientific discovery. Using the STM, we imaged a lot of materials that we were able to fabricate by combining theory and microscopy. Normally, you can oxidize metals like copper and copper oxide or iron oxide or silicon dioxide, aluminum oxide. The oxygens in the column of the periodic table, these other elements have similar properties to the oxygen. So we did it with selenium, and I will show you patterned platinum diselenide. You just put selenium on platinum, and then you heat it a little bit, and you get this material. It took us a long time to figure out what the material is. We had to do a STEM image from the side, so we could see the substrate and the monolayer at the top of platinum diselenide. It was published in 2015, and then additional experiments showed that if you anneal it at 400 degrees Celsius, very carefully, and it took a while to figure this out, how to get perfect triangles, but you get two different triangle structures of two different arrangements of the atoms in the material, the 1H and the 1T structure. And then if you go back and lower the temperature, you can recover the original one, but you have to add seleniums. So it was evident that these triangles are formed by having selenium vacancies, and we demonstrated with theory indeed that if you have a lot of selenium vacancies, they pattern out like that and give you the triangles. We wanted to do this to pattern so that you could use potentially two different molecules on the two triangles and have catalysis, for example, or sensing or something else, to have two possibilities in the same material. On this pass, every molecule we tried all went to the same kind of triangle, both experimentally and theoretically. We tried copper, and we got a very different pattern. In the monolayer copper selenide, we had little holes of triangles, either in this orientation or in this orientation, with this kind of boundary that you can see here like that. Here is an image, a close-up image of one triangle. And in this case, we succeeded. If we put large molecules, they go on the terraces. And if we use just iron atoms, they go in the holes. Here is the images of the large, and I don't have the image here. I realized as I was talking before that the iron atoms go in the holes. And the last one we did, silver selenide, a very different pattern. And here is the boundary. And if you use this molecule alone, pentacene, it goes right on the boundaries and forms these corals. If you use this molecule, it goes everywhere and forms patches. And if you use them together, you get the patches inside the corals. So another demonstration of selective patterning and selective process. And that was the end of the story. So I am done. Thank you for sticking around and seeing the end of the story. And you can ask me questions now if you have.
Yeah, thank you, sir, for your wonderful presentation. So we have two questions in the inbox. So the first is that how did we measure the size of atom?
How do you measure the size of the atom? It's in the images, because you have a scale in the images. In the STM, you image this, for example, by moving the tip. So when you image it, you have the tip coming down and you move it, move it, move it, move it. So you know how much you move it. You know these distances. In the materials, you also know other things. If you go back to graphene, we know from X-ray diffraction and others, we know what the distances between atoms are. So you can see here that this distance is 0.25 nanometers, is a known distance of the atomic structure. And we're just imaging it here. Okay.
Okay, sir. Thank you. There is another question. So what is the passive nanostructure?
What is?
Passive nanostructure. Passive.
I can't understand it.
Okay, so there is an active nanostructure and
passive.
Active.
So an active nanostructure is one that would react chemically, as opposed to being like gold. Gold is not active. It does not oxidize. So it's surrounded by oxygen molecules, and it does not react with the molecules. So chemically active, that's what we need. It can participate in chemical bonds or not.
Okay, so this may be the last question. Can you explain the medical application of nanotechnology?
Medical applications, I showed you two, where you use, here's nanoparticles that carry medication inside them, and they go, and with these molecules on the outside, they can attach themselves preferentially at different places inside the body, and they break up and they release the medication exactly where you want it. In the case of therapy, gold atoms like this absorb light very well, very easily, and then re-emit it. And you can use light to actually burn cancer cells, to fry them. And the next example was when we used on nanobiotics as a process where they put nanoparticles inside the tumor, and the nanoparticles absorb the X-rays very efficiently, and then they re-emit them inside the tumor. So the tumor gets a lot more X-rays than the surroundings. So you minimize about a factor of 9. So you can reduce your dosage by a factor of 9, and your nanoparticles will provide the full strength that you want, so you don't do as much damage outside. As you know, radiation of cancer, it doesn't just kill the cancer, it does a lot of other bad things around it. No matter how much you target it, the surrounding area is damaged. So there are many, many other applications. In nanomedicine is a big field now. And that's it. No more questions?
Yes, so thank you, sir. Thanks again for giving us this opportunity. So it's my pleasure and privilege, actually, sir, to host you, sir. So
thank you. It
thanks
was my
again.
pleasure.
My pleasure, sir.
Have a good evening. Bye-bye.
Bye-bye, sir. See you, sir.